So we're going to be using the graph of f of x here to make two graphs of capital F of x. So we're going to be using the integral and the awesome fundamental theorem of calculus. So I'm going to scroll this down a little bit here so we can see all three pictures at once, okay? So right here, I'm looking at a gorgeous graph, and I can see in number one, we're letting f of 0 equals 0, and in here f of 0 equals 1. So using FTC can never get enough of the good stuff. Integral from a to b of f of t dt, that's going to equal f of b minus f of a. All right, so let's start with 0 to 1. I mean, that seems like a pretty good place to start. So I'll say the integral of 0 to 1 of f of t dt, that's going to be equal to f of 1 minus f of 0, correct? Now, lovely triangle I have here. The area underneath the curve from 0 to 1 is going to be 1/2 times 1 times 2, which is 1, right? So in two cases over here. First case, this one, 0 to 1 of f of t dt equals f of 1 minus f of 0. This part equals 1. F of 1 is in question, minus f of 0 is 0. So that means f of 1 is 1 here. So I can plot the point 0, 0. 1, 2, 1, 2, 3, 4. 1, 2, 3, 4. Wow, that's hard today. Okay, there's that point right there, 1, 1. And if I do the same thing with the integral, you can go 0 to 2, you can go 1 to 2. It does not matter. Let's see here. We'll go 1 to 2. We'll build. Okay, so f of t dt equals f of 2 minus f of 1. So then you can see already it's the same shaped triangle. So 1/2 times 1 times 2. F of 2 is the question. F of 1 we recently learned was 1. So this is 1 equals f of 2 minus 1. Add the 1 over and you will get 2. 1, 2, 3, 4, 2. 1, 2, 3, 4, 2. Do, 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 do. There we go. Now, the exciting part. If my first derivative, right, this is what I'm looking at here, is increasing, that tells me our original function was concave up. And if my derivative function is decreasing, then I can see that my original function was concave down. Oh, that's a gorgeous graph. So now coming over here, all that changes is now f of 0 is 1. So now f of 1 is 2. So when I plot this on this graph now, 2, 3, 4, starting right there, this is going to be up at, I'll go by 2s. Sorry, folks. 1, 2, 3. 1, 2, 3. So in the first second, we're right here. And then we're up here. And then we're going to be all the way up there, because I'm going to add 1 again. Still increasing, concave up, then decreasing, concave down. Pretty darn beautiful. Okay, in the next graph, I'm going to have you try this one. Notice the same setup here. All of the first 3.5 seconds are at a constant, so that'll be a straight line. And then we have this decreasing function right there, which means, I'm sure you all just said concave down. So this is an AP question off some year, and it says you're going to start with the fact that f of 2 equals 3. You want to sketch the graph, and you want to label at least 4 of the values. So here we go. It's going to be exciting. I'm going to start with the graph right there. Okay. and they're going to tell me f of 2 is 3. That's helpful because I can see, I'm going to make this a little bit smaller for myself here. Okay, I'm dealing with f of 2, and up, look right there. So I'm going to write an integral, start with 0 to 2 of f prime of x dx is going to equal f of 2 minus f of 0. All right, so they're telling me the area from 0 to 2 is 2. Excellent. F of 2 is 3, so f of 0 is the question. Subtract 3 over, I'm going to get negative 1 equals negative f of 0, so f of 0 is positive 1. So let's start by plotting that. F of 0, 1. And I'll cover that, label it 0, 1. Okay. Then we can plot the point 2, 3. All right. We can see here, now we're going to deal with this section right here. We're going to go from the 2 to the 6. So let me get myself some more room. So I'll write an integral from 2 to 6 of f prime of x dx equals f, these should be capitals, we'll get over that real quick, f of 6 minus f of 2. F of 2 we have recently learned was 3. F of 6 is in question. Now here's where it gets stressful. The area right here is 7. Okay, if I'm talking about how much space it's taking up, but if I'm doing the integral, that's going to be negative 7, correct? So then add the 3 over. F of 6 is, add 3 is negative 4. Okay, so I'm over here, so 2, 3, 4, 5, 6, and we're going to be down to negative 4. Okay, so now we have to talk about, we need another point. We have more work to do. Hold on. Okay, integral 6 to 8, all right, of f, capital, f prime of x dx equals f of 8 minus f of 6. We recently learned f of 6 is something, negative 4. So I have negative 4 over there. This area is 4. So 4 equals f of 8 plus 4. Subtract the 4, f of 8 equals 0. Bing, bing. There we go. So we've got 8, 0. Okay, so a couple more things we have to discuss. Max and mins and concavity. Looking at the derivative graph, we can see there's a critical point at 2 and a critical point at 6. We'd also worry about endpoints if we were talking about globals. So at 2, it goes from positive to negative, which means there is a max. Well, that's good because it looks like our graph goes up to the highest point. And at 6, it goes from negative to positive, meaning that there is a min. Again, excellent, because my graph goes really low there. The last thing we have to break up now is concavity. So remember that this is the derivative graph. If the derivative graph is increasing, then we know my original graph is concave up. So right there, 0 to 1, concave up. Okay, concave up. And from about 4 to 7, 4, we'll get to that. Okay, 4 to 7 is going to be concave up. And then the rest of this beautiful graph is going to be concave down. All right, so concave down, here we go. Up, still concave down. We're going to do that till we get to 4, right? And then I'm going to switch it back. Concave up, concave up, concave up, till I get to 7, and then it's going to switch again. Back to concave down. Now that is just a gorgeous graph if you ask me. All right, have a great night, except you have to watch 6-2 now. So almost have a great night.